From a 400-foot tower, a bowling ball is dropped. The position of the bowling ball, S of t, is negative 16t squared plus 400, where t is greater than or equal to 0 in t seconds. Find the instantaneous velocity of the ball at 2 seconds. Well, recall that instantaneous velocity is simply the derivative of position. Okay, so velocity is equal to s prime. So in our case, that's negative 32t. So s prime of 2 is negative 64 feet per second. The average velocity for the first 3 seconds. Well, average velocity, there are a couple ways we could do that. We could actually do the integral, do the average value of the velocity function, or we could just evaluate the position function to see how far did the ball travel in 3 seconds. That's the way I'm going to do it. I'm going to find the position at 3 seconds and the position at time 0 and divide that by 3 minus 0. So effectively, I'm just doing a secant line. And I'm finding the slope between them, the two endpoints. S of 3 is 256. S of 0 is 400. Divide that by 3. We come out with negative 144 over 3, which is negative 48 feet per second. Next, when during the first 3 seconds the instantaneous velocity is equal to the average velocity. Now, nowhere in here does it actually say this, but I just wanted to point out that this is essentially stating where the mean value theorem is going to hold true. Remember, the mean value theorem says for a function that's continuous and differentiable on an interval, there must be a spot where the instantaneous rate of change is equal to the average rate of change. Well, that's what we're saying here. We're trying to find a place where the instantaneous velocity is equal to the average velocity, and we know, because it's just throwing a ball off a building, that the function has to be continuous and differentiable. So we need to set our derivative equal to our average and solve for t. So of course, just divide both sides by negative 32. So t is 1.5 seconds. Next, the acceleration at 3. Well, remember that acceleration is the second derivative of position. So the next derivative down would just be negative 32. So s double prime of 3 would just be negative 32, and the label or the unit would be feet per second squared. Finally, when does the ball hit the ground? Well, of course, now we're back to position. We want to know when our position function is equal to 0. So negative 16t squared plus 400 is equal to 0. First step probably just be to move 400 over to the other side. So we have negative 16t squared equals negative 400. We could divide both sides by negative 16, and then we end up with t squared equals 25. So t is going to be 5-second mark. Now you may think, well, couldn't it be plus or minus 5? Remember, in the original function we were told that t had to be greater than or equal to 0. In this case, we're talking about moving along a line. Okay, so it says Mr. Danielson begins moving along a straight line with a position function of s of t equals t cubed minus 6t squared plus 9t minus 1. When is Mr. Danielson moving left? Change directions. Now, I'm going to start by just kind of analyzing velocity. I'll go back up there and answer those questions. But let me just start by talking velocity. Velocity, remember, is the derivative of position. So in our case, that's 3t squared minus 12t plus 9. Do some factoring here. I could take a 3 out of everything. Be left with t squared minus 4t plus 3, which I could factor to be 3 times t minus 3 times t minus 1. Okay, so this is my kind of key velocity function. And it turns out we've got some critical points here of 1 and 3. So if I put that on a number line, let me just quickly do that right here. We've got 1, 3. If I do a little sign analysis, if I plug in a number less than 1, I get a negative times a negative, which is positive. If I plug in a number between 1 and 3, maybe 2, I get a negative times a positive, which is negative. And if I plug in a number bigger than 3, I get a positive times a positive is a positive. Now moving left is usually considered moving backwards. Okay, so we could even maybe make a little note here that you're moving back. You're moving to the left. That happens whenever velocity is negative. You're moving backwards when velocity is negative. So that happens between 1 and 3 seconds. Okay. Now, thankfully, I never had to talk about the fact that t should be greater than 0 in this case, but of course we would normally just consider that we do have a stopping point here at 0 because these position functions usually assume t is greater than or equal to 0. Next, when does Mr. Danielson change directions? Well, we have a velocity function that tells me that I was moving forward from 0 to 1, then backward from 1 to 3, then forward again from 3 on. So I change directions at t equals 1 and t equals 3 seconds. And again, if you were asked to justify that, you'd say, well, that's where velocity changed signs. Now finally, where is Mr. Danielson speeding up? Well, speeding up, we talked about in class, it's when the velocity graph is moving away from 0. But since I don't have a graph and I really don't want to make one, I'm going to use the other way to tell if something's speeding up or slowing down, and that's to analyze velocity and acceleration together. So let me do acceleration here quick. Acceleration is s double prime t. So in my case, that's 6t minus 12. So the kind of big important point here is going to be t equals 2. So again, let me put that on a number line. Okay. If I put in a number to my second derivative less than 2, I get a negative. If I plug in a number larger than 2, I get a positive. Now, something is speeding up. Okay, I didn't ask to justify, but I'm going to make this note up here. When both velocity and acceleration have the same signs. And you're slowing down when they have opposite signs. Okay. So we're speeding up. Let's kind of compare these two graphs if we can. So starting, again, this is probably there's a cutoff here probably at 0. Right. So let's look at these kind of one next to the other. From 0 to 1, velocity is positive, but from 0 to 1, acceleration is negative. So they have opposite signs. I'm slowing down. From 1 to 3, velocity is negative. Well, from 1 to 2, acceleration's negative. So since they're both negative there, we are speeding up. Okay? So from 1 to 2. That'd be one spot I'm speeding up because the signs agree. Okay? Well, here it says from 2 on, it's positive. Well, of course, from 2 to 3, velocity is still negative, but from 3 on, velocity is positive. So from 3 on, I'm speeding up. Okay. Now again, there are a couple ways you can justify speeding up and slowing down, but probably the easiest way, and the way you'll see the most often in the AP exam, you just analyze velocity and acceleration together. And if they have the same sign, then you're speeding up. If they have opposite signs, you're slowing down.